Here we're looking at the weight of an object. We're imagining an elevator in a skyscraper that takes 4 seconds to reach its cruising speed of 10 meters per second. A 60-kilogram passenger gets aboard on the ground floor. We want to know what is the passenger's weight before the elevator starts moving, while the elevator is speeding up to its cruising speed of 10 meters per second, after the elevator reaches its cruising speed, and while the elevator is slowing back down, presumably in the same 4-second span. And we said that the weight of an object is related to the normal force that that object would feel. So if you have a person in an elevator, that person has gravity pulling them down, and that person has a normal force from the floor pushing them up. And so if we look at Newton's second law, that tells us that the sum of the forces equals mass times acceleration. If we assume upward as the positive direction, which is typical, then we say that the normal force of the elevator on the person minus gravity, because gravity is downwards, it's against the direction of motion, that would have to be mass times acceleration. Or the normal force pushing up on the person from the elevator floor would have to be mg plus ma. There's a common m that can be factored out. If you factor a g out, you can factor a g out of here, but you have to divide by g as well. And that's where we got the equation that we saw in the lecture, in the lesson, that the normal force that the person feels is 1 plus the acceleration in the y direction over g. And so this normal force is provided by the floor of the elevator. If it was a flimsy floor of the elevator and you tried to accelerate upward too quickly, the bottom could tear out, the same way that if you have a grocery bag and too many groceries in it, you could tear the bottom out. Similarly, in the lesson we talked about as if there was a scale there. In that case, the scale would be providing the normal force holding our person upward, and in some cases accelerating our person upward. So we're first interested in looking at the acceleration before the elevator starts moving. So if we're talking about before the motion begins, then the acceleration of the elevator is 0. And if we use the equation we just derived, then in this case, our weight, our normal force, will just be mg 1 plus 0. That term goes to 1. And our normal force is mg, which makes sense. If we're not accelerating, if we're not moving, then there's nothing special going on. Our weight, which we'd feel as the normal force pushing us up, is just mg. For part B, we're told that the initial velocity is 0, the final velocity is 10 meters per second, and the time is 4 seconds. And from there we can say that the acceleration has to be 2.5 meters per second. Here it's positive because we're going upwards. We're accelerating from 0 rest to having an upward, a positive velocity. So going back to our equation, here the mass is the mass of our passenger, that's 60 kilograms, g is 9.8, and the acceleration is the acceleration we just found. We find that the weight, which should be a force, is 738 newtons. That's kind of hard to visualize, and so we can divide out the 9.8 and say it's as if our passenger weighs 75.3 kilograms. Considering that they usually weigh 60 kilograms, to say that they feel 75 kilograms worth of force means that they weigh about 25% more than they normally do, which is a significant amount. For part C, we're at our cruising velocity. And so if the elevator's traveling upward at its cruising speed, then its acceleration is 0. Once you reach a cruising speed, you're not accelerating anymore, and so there's no more extra force needed to speed you up. And so the normal force, the weight that you would feel, would be your regular weight. Basically, in the situation of C, when you're moving at a constant rate, that's the same as A. Both of those situations, whether you're not moving at all or moving at a constant rate, those are both inertial frames. And so the regular physics works. In part B, you are speeding up. You are not in an inertial frame, and so you have something different than normal happening to you. And in the last situation, in D, we would presumably have the same acceleration, but negative. We'll assume our acceleration will be a negative 2.5 meters per second squared. In that situation, we can use the same equation that we used before. And in this case, our weight would be the normal force that we feel, which would be 438 newtons, or like before, that's equivalent to feeling 45 kilograms. So we only would feel 3/4 of our weight that we normally would.